Hello everyone, I'm Dr. Nandy. Welcome to my YouTube channel Ecstasy of Physics. In this video, we are going to talk about the momentum free response questions. These questions we have got in 1995 AP Physics 1 test. As shown above, a 0.2 kg mass is sliding on a horizontal frictionless air track with a speed of 3 meter per second when it instantaneously hits and sticks to 1.3 kg mass initially at rest on the track. So let's analyze the sections what is given. So first of all is given that a 0.2 kilogram of mass. So let's consider this is m equal to 0.2 kg, this one, and its velocity is given here, that is 3 meter per second, and it hits with a sticks to a 1.3 kilogram of mass initially at rest. So there is other mass we can consider. Let's say this is m1 and there is other mass m2. This one is given as 1.3 kg and the initial velocity of this block 1.3 kg block, that is 0. It is in rest condition. The 1.3 kg mass is connected to one end of a massless spring which has a spring constant. So spring constant is given here, that is 100 Newton per meter. The spring is connected with the one end of this 1.3 kg mass. Now the other end of the spring is fixed. So this side is representing the fixed end. Determine the following for the 0.2 kg mass immediately before the impact. So in the first one, we have to find out the linear momentum. In the first section, linear momentum. Linear momentum of what? Linear momentum of 0.2 kilogram of mass. Where this 0.2 kilogram of mass is there, this is representing, they are talking about the m1 mass, that is 0.2 kg. Before the impact means before the collision. So before the collisions means what could be the momentum of this section? We have to consider that before the collision means when the block will be located here, that m1 mass will be located here. But what could be the speed? The speed, it will be same as 3 meter per second. Why? Because of it's given that it's a frictionless air track. Since it's frictionless, so there will be no loss in the velocity. The velocity will be maintained as same, and due to which we'll be considering the linear momentum before the collisions of the first block, that is m1 times v. m1 is given as 0.2 kg times by 3 meter per second, so it is 0.6 kg meter per second. That's the linear momentum of the first block before the collision. Now let's move on to the question 2. First part 2, it's kinetic energy. Kinetic energy expressions, that is half into m1 into v square, then half into, that is 0.2 kg times by v square. So if you do these calculations, you'll be getting, so that would be giving 0.9. What would be the unit of kinetic energy? That is joules. Now let's move on to the questions part B. So in the part B, they are asking determine the following for the combined masses immediately after the impact. So what would be the linear momentum after the impact? And after the impact, so we can apply the conservation of momentum, and according to conservation of momentum, we know that total momentum is always conserved, which means that they are asking for the determine the following for the combined masses immediately after the impact. Combined masses means that two blocks will be moving combinedly. In that case, what would be the linear momentum? We know that momentum is always conserved, and since the momentum is conserved, we can say the total momentum, it will be always remaining same. So whatever will be the momentum before the collisions, that will be same as the momentum after the collision. So what could be the momentum before collisions? The momentum is already we have computed, that is p equal to 0.6 kg meter per second. The momentum of the first block before the collision, that is representing the total momentum, since the velocity of the second block before collision, it is 0. That means for the first part B1, the momentum is 0.6 after the collision as well. Now we have to determine the second part, the kinetic energy. To determine the kinetic energy, we have to know what would be the combined velocity of these two blocks, and in that case we can apply the conservation of momentum to find out the combined velocity. According to conservation of momentum, total momentum before collision, that is equal to total momentum after collision, since the two masses are moving together. So I'm just combine m1 plus m2 times by, let's say the combined velocity, it is v prime, so it's v prime. So from there you will be getting v prime equal to 0.6 by m1 plus m2. So m1 plus m2 is, m1 is 0.2 plus 1.3. So you will be getting how much? 0.6 divided by 1.5, that is equal to 0.4. 0.4 meter per second, that's the velocity after the collision. Now we have to find out the kinetic energy after the collision. Kinetic energy final, that is equal to half into combined masses, it's m1 plus m2 times by v prime squared. From there we are getting half into combined masses, already you have got, that is 0.2 plus 1.3, and the v prime, it is 0.4 square of that. So we'll be getting, it is so we have got 0.12 joules, right? So in the third part, it's given that after the collision, two masses compresses the spring. So we have already got the combined velocity, that v prime, that is equal to 0.4 meter per second, and the spring is going to compressed. So let's say the spring is compressed by a distance that is equal to x. We have to determine that what will be the maximum compression distance of the spring. To get this value of maximum compression, again also we can apply the conservation of energy. According to that conservation of energy, this total energy when the spring started, when the spring was not started its compression, the total energy at the initial point, that will be considering that before started compressions of the spring, and the total energy at the final point, that will be representing that at the extreme condition when this spring is completely compressed, and in that case the velocity of the block, it becomes 0. So total energy at the initial position, that is equivalent to the kinetic energy, and total energy at the compressed situation, that's represented by the spring potential energy. Kinetic energy, already you have computed that, that is 0.12, and that is equal to spring potential energy is half into k into x squared. So from there we have to find out the value of x, that is twice of 0.12 upon k. K value already is given in the statement, that is 100 Newton per meter. This is the k value, 100 Newton per meter. So it's 100, and x is square root of that. If you do this calculation, it will be giving 0.049 meter. So which means you can say it's 4.9 centimeter the spring is going to compressed. A track consists of frictionless arc. So initially the frictions in between that x and the y track, that is frictionless. So it's given that mu k equal to 0. Mu k stands for the coefficient of frictions of this ramp xy. It's frictionless track, that is mu k equal to 0. Now which is a quarter circle of radius r. So it's the radius of curvature, it's given that, that is equal to r. And a rough horizontal section yz. So from here y and up to z, that is a totally rough horizontal section, and rough means it will be having the certain frictions. Coefficient of frictions is given that mu k equal to mu. Now the block A of mass m, here the block A is located, whose mass is given as, that is equal to capital M, from rest at point x. So initially the initial velocity of the block at the point x you can consider is 0, since it's given that it is released from rest. Slides down the curved sections of the track and the collides instantaneously inelastically with the identical block B at point y. So they have used few terms. collide instantaneously and inelastically. Inelastically means that only momentum will be conserved but the kinetic energy will not be conserved. And instantaneously means the collisions in between these two blocks, it is not for a long durations of time. They have just instantly collide and they move apart. Now the two blocks move together to the right and sliding past point P. So the two blocks move together. So it's given that they are moving together means combinedly they will be having the common velocity and sliding past point P. So it is passing through the point P. So P point is located here, which is at a distance of L from the point Y. So it's the distance is capital L from the point Y. Y to P distance is given as L. Now the coefficient of frictions between the blocks and the horizontal part of the track, that is given as mu. The coefficient of frictions is mu here. Now express all the answers in the form of this given parameters. Now the first one, determine the speed of block A just before it hits the block B. Where is the B block is located? B block is located initially at the position Y and A block is located at the position X. So we can apply to determine the speed of the block A, we can apply the conservation of energy. Conservation of energy. By applying the conservation of energy in between the point X and the Y. So Y point I will be considering just before hitting with the block B. So in between the point X and the Y. So at the point X, initially the block it is in rest condition. So according to conservation of energy, we can say the total energy at the point X, that is equal to total energy at the point Y. It's kinetic energy and gravitational potential energy. Similarly, kinetic energy and gravitational potential energy at the point Y. Now the kinetic energy at the point X, that we can write it down, is 0 because the velocity it is 0. What will be the gravitational potential energy? For that we need to define some datum position. So let's consider this horizontal position. I'm considering the datum section, means the reference line. With respect to that, what would be this distance? Here they have given the radius of curvature, that is equal to r, which means the distance in between the datum line or reference line to the point X, that should be r. So gravitational potential energy, it becomes the mass times gravitational accelerations times by h, and that is equal to, since at the point Y the height h should be 0, so we'll be considering that kinetic energy it should be half mv squared. And finally, to obtain the velocity before the collisions of this block, this mm is getting cancelled, v it becomes square root of twice into g into h. But this h we need to substitute by, because presently this h we are considering same as r, so we need to substitute by r, that is equal to twice into g into r. That's representing the expressions of the velocity of the block A just before it hits the block B. Let's move on to the next part. In the next part, it's given that they are asking determine the speed of the combined blocks immediately after the collision. So here we can apply the conservations of momentum. Since it's the inelastic collision, but we can apply the conservation of momentum, that is valid for elastic and inelastic for both the collisions. Apply the conservation of momentum here. Conservations of momentum. According to conservation of momentum, the total momentum would be conserved just before the collisions and the after the collision. So before the collision, just think about the block A would be located here and it is having the velocity v, and block B initially it is in rest condition, and after the collision both the blocks are merged together and they are moving with the common velocity. So that velocity I am considering as v prime. So here we can say before the collision the block A is having the velocity v and the mass is m. So mass times velocity, and block B is having the mass is m but the velocity is 0 before the collision. After the collision, since they move together, we are going to consider the common mass, that is m plus m times by velocity, that is v prime. So from there we can say that mv, that is equal to 2m into v prime, and v prime it's become mm is getting cancelled, it v by 2. Expressions of v, that is equal to square root of 2gr, we can replace in this equation half of square root of 2gr, and finally we'll be getting the expressions, it is square root of gr upon 2, that is representing that v prime. So this v prime is representing the determine the speed of the combined block. So this is the velocity after the collision of the combined system. So in the third section it's given that assuming that no energy is transferred to the track or to the air surrounding the blocks, determine the amount of internal energy transferred in the collisions. No energy is transferred to the track or to the air surrounding the block. That means there is no frictional energy loss is being considered during the collision. So determine the amount of internal energy transferred in the collisions. Amount of internal energy transferred in the collision during the collisions only. So here what we can have the initial kinetic energy of the block A, and we have the final kinetic energy of the two block system. If we take a difference, if we make the difference in between the kinetic energy before the collisions and kinetic energy after the collision, then we can determine that how much is the internal energy transferred in the collisions. So here for the third part C, already we have defined that after the collision the velocity of the combined system, that means the combined block, that is square root of gr by 2. Now we can define the kinetic energy before the collision. So we can say kinetic energy initial, that is half into m into v square, that is for the block A, and kinetic energy final. Kinetic energy final means after the collision what is the total kinetic energy of the system. So that is half into what is the mass of the system. Presently two blocks are moving together, so total mass of the system is m plus m is 2m times by v prime square. And so now we can easily define half m, and this v value we have got earlier, that is square root of 2 into g into r from the first part. So that we can substitute in this equation, instead of v square it is 2 into g into r, that will be equal to mgr. And in the second part this is 2 is getting cancelled, m into v prime square, and v prime equal to this one square root of gr by 2. So if you make this square you will be getting gr by 2. Now the amount of internal energy transferred in the collisions, so you can say that delta change in kinetic energy, that will be equal to kinetic energy initial minus kinetic energy final. Kinetic energy initial, that we have got m into g into r, and kinetic energy final is half into mgr. If you make a difference you will be getting half mgr. That's the amount of internal energy transferred. That is the answer for the part C. So here is better to say will be like negative mgr, negative half mgr, because of its kinetic energy I have taken the initial minus final. So in that case we will be saying that this is the amount of energy loss. This is the amount of energy loss from the system. So technically after collision, since the velocity is becoming like v prime combined velocity, so in that case there will be a certain amount of loss due to the inelastic collision, and that loss it can be represented by half mgr. So in the part D, determine the additional thermal energy that is generated as the blocks move from Y to P. So just follow the diagram. The blocks have moved from the Y to the point P. In that case, how much is the amount of thermal energy is produced? Here basically the thermal energy is represents that amount of loss due to the friction. The frictional energy loss will be referring that amount of thermal energy. So thermal energy, it can be represented as the work done due to frictions, and work done due to frictions means is the frictional force times by the displacement, and the displacement is given as that is equal to L, and amount of frictional force will be how much? That will be mu is the coefficient of frictions, that's given as mu, that's coefficient of frictions times by the normal reaction force times by L. Now the thing is, the frictional force will be exerted will be in the opposite directions of its motion, and the block got displaced in the forward directions from Y to P. An actual formula we can use that force times displacement into cosine of theta. By this, presently this theta equal to 180 degree. Since the frictional force exerted in the opposite directions of its motion and the block it is moving in the forward direction, and cosine of 180 degree here. Mu into what would be the normal reactions? If you are going to draw the combined system, the total mass is 2m, due to which the total gravitational force, that is 2 mg, which means that normal force, that is also Fn. Now along the y directions or vertical direction, since there is no net force exerted, we can say normal force Fn, that is equal to 2 mg. So you can substitute Fn, that is equal to twice of m into g times by L into negative of 1. Cosine 180 degree is negative of 1. So from there we are getting negative mu 2 mu m g L. So that's the expressions of the thermal energy, and the negative sign is basically representing that amount of loss in terms of joules we are getting.